Hello, kids. Once again, we are going to go over the summer packet problems, and this time I am starting with some more of problems 3, problem 4, and then I'm going to skip to problem 7. So 3, again, if you remember, was factoring, and I tried to highlight to you again that factoring is a foundational skill that is underneath so much of what you do in all higher level math and science as well, and really all over. Factoring is breaking down a complex problem into little parts, right? I do that all the time. So instead of going overwhelmed by a big problem, I try to break it down. I break a text down in English. I break down a DBQ in history. When my car breaks down, right? I try to, oh my God, what do I do? Try to factor the problem. Do I need to call somebody? Can I fix something myself? Do I need to get off to the side of the road, right? Factoring is really a way of thinking, and math factoring is a way to get your brain to practice that concept. So we went over on the last video some quadratic factoring and difference of two perfect squares, perfect square trinomials, that kind of thing. And one of the last problems we did was a less used technique called factoring by grouping. Again, don't stress if that's not at the top of your list, but do stress if factoring quadratics and all the special quadratics like difference of two perfect squares and perfect square trinomials you're not fluent. If you're not fluent in those, that's where you need to spend your energy. If you're already fluent in those and you're very good with those techniques, yes, then start making sure factoring by grouping. But if factoring by grouping is very hard for you, you need to work on it, but it is not as high of a focus or high of a need as the quadratics. So again, how I know factoring by grouping is something I want to try is when I have more than 3 terms. Of course, I always look to see whenever I have terms, can I pull out something in common? And I can't pull anything in common out of all 4 of these. But if I group this group, if I use, right, and that's just the associative property of addition, and notice that unlike the last problem, I have a plus here instead of a minus. That makes my job a little bit easier. Now, when I look at what's in common in this group, I pull out an x, and I get an x minus 3. What I would like to do is to get an x minus 3 over here as well. Is that possible? Can I pull something out of here such that I'm only left with an x minus 3? Well, if I pull something out of here and only an x is left, I'd have to pull out a 2y. Multiply the 2y, right? And since this is all positives, positive 2y times x is 2xy. Positive 2y times negative 3 is negative 6y. Now think of this as one big group with a plus sign in between, and pull out of the group the x minus 3. So pull the x minus 3 out front, and then what's left? You divided the first term by x minus 3, and all that's left was x. You divided the second term by an x minus 3, and all that was left was a 2y. And notice to undo the division that I did here, this is technically what you're doing, right? You multiplied by x minus 3 because that is multiplication by 1, and that's why pulling out in front works. Okay. Both of these are prime. There is nothing else I can pull out of this group or this group. And just a reminder, in algebra, we agree that a factor is prime if it does not break down into rational factors. All right, now I see 2 terms here with a minus in between. So I think, is this the difference of 2 perfect squares? Well, these aren't 2's, but x to the 4th is a perfect square, right? But the 3 is in my way. Pull the 3 out front, break down the difference of two perfect squares. And then make sure that you have prime factors. 3 is just a multiplier, it's not a factor, right? So that's fine. X squared plus y squared, this factor here is the sum of perfect squares. The sum of perfect squares is prime. But this is another difference of two perfect squares. This factor can be broken down further. So that is the complete factorization. Again, to remind you, if you had 12 and somebody asked you to factor it and you said 6 times 2 and your teacher said that's good, but I need you to break it down further, you would break down the 6 into 3 times 2 and you would leave the 2 alone because it is prime. And remember, for integers, we agree what's prime is there are no whole numbers that you can multiply together to get a number, right? So for instance, 6 is not prime because 3 and 2 are two integers that I can multiply together to get it. We call 2 to get 6. 2 we call prime because there's only 1 in itself, but I can multiply 4 and a half, right? 4 times 1/2 is equal to 2. So why do we call 2 prime? Well, because we've agreed that a number is prime if the only factors are integers, right? And 1/2 is not an integer. For algebra, we have agreed that a factor is prime if it cannot be factored into rational factors. Okay. This is another one of the cubes, right? I told you again, just like factoring by grouping, factoring cubics by a pattern is a nice thing to know and a nice thing to remember. But if you forget it, it is not crucial. It's something you can look up. It's not tested that heavily, but this is the difference of two perfect cubes. 4 cubed is 64, x cubed is x. And 1 cubed is, of course, 1. The difference of perfect cubes factors into two factors, a linear and a prime quadratic. 4x and 1 goes there with the minus sign. And then unlike the problem I did for you in the previous video that had a plus in between here, it was the sum of perfect cubes. Since it is a minus, all the terms in the prime quadratic are positive. And you take 4x and square it. You take 4x and 1 and multiply it together. And you take 1 and square it. And we are done. R is a perfect square trinomial. This is one of these things that if you do a million of these problems, you see that right away, right? 9 is a perfect square, 4 is a perfect square, 3x times 2 is 6x, doubled is 12x, done. All right. This is a regular quadratic with a leading coefficient that is not 1, but it factors into rationals. You should not be using the quadratic formula on that. This one is cubic with them. Oh, and then I've got a fourth. Ooh, I need to see if I can pull something out front here. A 5 is common and an x is common, leaving me with x squared minus 4y squared. I'm sorry, 4y to the fourth. 5x is prime, but this second factor is the difference of two perfect squares. And the difference of two perfect squares pattern is one that you should know very well. Okay, and if you doubt me, multiply those all out and you will get 5x cubed minus 20x y to the fourth. These last two problems are kind of cool because this is something that if you have done a gazillion quadratics, if you have factored lots and lots of quadratics, you'll look at this and your brain will want to see this. That's what your brain will want to do, right? Because your brain loves to make connections and it loves to see patterns. So notice that the original problem is very similar to the one I wrote in red. It's got 3 terms. Instead of a squared and a first, it's a fourth and a second. So how would you factor the red one? Hopefully with lots of fluency. You would fairly quickly get to this. Those are the factors of the red expression. But I wasn't given the red expression. I was given the one with x to the fourth and an x squared. Well, look what happens if I do this. Isn't 3x squared times 2x squared 6x to the fourth? And isn't 3x squared and 10x squared equal to 13x squared? And isn't positive 5 times positive 1, 5? When you multiply these 2 red factors together with the squared that I added, I get this blue, or the original expression. Therefore, the red factors must be the factors of the original problem. Can you see how you would do this way is the same one? Forget about the fourth and the squared for a second. Now add and see if I'm right. 5x squared times 2x squared is 10x to the fourth. Negative 15x squared and positive 8x squared is negative 7x squared. Positive 3 times negative 3 is negative 12. Therefore, I must have factored correctly. And I keep going back to this concept of if someone asked you to factor 12 and you wrote 5 times 2, you would say they're not right. Because when you multiply 5 and 2, you do not get 12. But when you factor 12 and somebody says 6 times 2, you agree with them because when you multiply 6 times 2, you get 12. These 2 blue factors are the factors of 10x to the fourth minus 7x squared minus 12 because when I multiplied them together, I got this expression. Right? It's not rocket science. That's all factoring is, right? You're not changing anything. You are only rewriting it in a broken down form so that you can attack each little piece at once. Cool? All right. Hopefully I have made an impression on you that factoring is really super important. One of the main things that you do at the beginning of, right, and early on in your math education is using factoring to solve. Now here I am only giving you quadratic equations to solve, right? So there are lots of equations that I would like to solve. Factoring is a key component to most of them, right? But if you can use factoring to solve quadratics, well, then you can extend that knowledge when I give you non-quadratics, right? So factoring is the method to solve. Now with solving an equation, those 2 words, remember earlier on we solved for a variable. That just means getting a variable by itself. When you solve an equation, you are finding values to plug in. To make the sentence true. To make truth. Whatever x I come up with, or x is, have to be able to be plugged in here and generate 0. So our strategy, they told me to do factoring. So number 1, I'm going to factor. Number 2, I'm going to use the 0 product property rule. Zero product property rule. And 3, solve pieces of the puzzle. So the first thing you need to realize is, now I know I told you that we're doing quadratics, right? So we're doing, all of these are quadratic. But what's special about polynomials is you're going to find 2 answers, right? You're going to find 2 answers because this is squared. And if you think about it again, graphically, quadratics either have 2 real solutions, the x-intercepts. They have 2 solutions, but the solutions are the same. They are repeated factors. Or they have no real solutions. Okay, like that or like this, right? Each one of these could be open, up or down, right? Two solutions in the set of real numbers. 2 solutions, but they are repeated. Same number, right? That are real. These quadratics also have 2 solutions, but they are not real. When you are asked to solve an equation, the default for AP and SAT and IB is over the set of real numbers. So sometimes I get some real cute little eager beavers, and they're like, well, I know if I get a negative on the square root, I can plot an I, and it's a complex number, and then that's great. I'm super impressed and so very happy that you know how to do that, but you're not following the directions. And so your answer would be incorrect. And this is part of the directions, as I said, of an AP exam, SAT, and IB exam, and you just won't read these directions, right? You're just gonna be so busy trying to get the test started. They're not gonna write out over the set of real numbers. You have to understand from the directions that when they ask you to solve an equation, the understood set that you're working with is real numbers. If they want to shrink your set of real numbers to, for instance, say just the integers, they have to tell you. If they want to expand the set of real numbers to include complex numbers, right, non-real numbers, then they have to tell you. If they don't say anything, you are giving them only the solutions within the set of real numbers. So it's a lot of verbiage, and I haven't even started the problems yet. So, all right, by factoring, I'm supposed to solve this. So this is where my fluency with recognizing this is a quadratic, and I've done so many of these, it does not take me long. It's a little bit annoying that I have a leading coefficient that's not 1, so I had to kind of guess and check a couple of times. I've done so many that my first guesses and checks are usually the right ones. So this parabola that opens up and has a y-intercept of 14 has 2 factors. Because my product is 0, if you have 2 things that are multiplied together to get 0, there's only one thing that can be true. The first factor must equal 0, or the second factor must be equal to 0. And then so that's the 0, so I factored, I just used the 0 product property rule. Notice there's no 10 product property rule. If this had been equal to 10, I could not go any further. you must, in order to use the zero product property rule, you must have 0 over here. That's like the pre-step. So now x is equal to -7/4 or x is equal to -2/3. So I don't exactly know what this parabola looks like, but I have a decent idea already. Right? Both of the x-intercepts are negative. I know it opens up. It's pretty narrow. And its y-intercept is 14. Done and done. Now, the quadratic formula is a formula that you do have to memorize. So you do need to, the fine print of the quadratic formula is that you will get right to this point. You jump the factoring and the solving and the zero product property rule, sort of. X is equal to the opposite of b plus or minus. There's where you get the two solutions. Plus or minus the square root of b squared minus 4ac. IB tests give you a formula sheet, AP does not. Now, this formula is great if you memorize it, but that it is incumbent upon you to know that what A, B, and C are. And the quadratic formula says if y is equal to 0, then x is equal to these values, the two values that you get. If you have a quadratic and if y is equal to 0. So again, if you'd had a 10 over here or a 100 or a 5 or a -2, you cannot use the quadratic formula until you are equal to 0. So the quadratic formula is plugging and chugging. I'm not going to go through it. The only thing I am going to, though, say is you don't need to go beyond this unless it's multiple choice and you don't see that answer, right? These are the two answers, or unless I need to graph, right? But I can simplify this by using my fraction knowledge. This is -6 on top of 6, plus and minus the square root of 84 on top of 6. So this is -1 plus or minus, and there's a 4 in there, and pulling out a 4 out of a radical gives me a 2 over the square root of 21 over 6. But then that, of course, is equal to -1 plus or minus, square root of 21 over 3. You do not have to simplify or rewrite what you get out of the quadratic formula unless somebody makes you. You do need to be able to visualize what these things are, right? The square root of 21 is a little bit smaller than 5. So -1 plus 4, well, so I should say this. So 4-ish divided by 3 is bigger than 1, right? So -1 plus a number that is 1-ish, right, is pretty close to 0, right? But -1 minus 1-ish is close to -2. Right? So that, you just have to, that's the only thing that simplifying helps me do, as opposed to -6 plus or minus the square root of 84 over 6. But again, I do know that just like the parabola before, I have a y-intercept of -4. This parabola opens up as narrow, but not as narrow as the 12 one. And I have two x-intercepts. One of them is pretty close to 0. And I'd use, figure out if it's exactly, right? Is it a little positive or is it a little negative, right? Now I want to erase this to do the completing the square work. So completing the square, solving by completing the square can sometimes save me time if factoring doesn't work. I look at this and I realize, oh, it doesn't factor into nice numbers, into the set of rationals, right? That's the symbol for rational numbers. Since this doesn't factor right? I tried for a second and I thought 2 times 2, 4 times 1, leading, nope, that's not going to work. I need to use the quadratic formula. But this is a pretty easy one to complete the square. Quadratic formulas swell, but what if I mess it up? What if I don't do the math right? Right? What if I plug and chug and don't get the right answer? So completing the square is not always the simplest way. Like I'm making you do completing the square here, right? And that really is to get you to practice completing the square. The method of completing the square is something you're going to use a lot in, you're going to use some in calculus, and you're going to use a lot if you keep going. For instance, in multivariable, you're going to use it a lot. It is a very handy algebra technique. All right, so completing the square, if you don't remember how to do that, now there's a couple different ways. Some people like to work all on the left side. I like to work on the right side, where I move the 4 over out of my way. And then I divide the middle term, right? I make sure I have a leading coefficient of 1. I divide the middle term by 2. I get -3. I square that and I get +9. And now here's why I like to move the original constant over to the other side, because I'm going to change the value of the left side, which reminds me that I must change the value of the right side by the same amount. And then what I have done, the reason you've completed the square is once you're at this place, you have birthed a perfect square trinomial. And I check to see that this -3 is equal to what's in my box here, and it is. And this is equal to 5. Now I try to get x by itself. To get x by itself, I need to undo the square that I just introduced. And remembering that this is a quadratic and I get 2 answers, I need to plus and minus the square root of 5 there. And I get x minus 3 is equal to plus or minus the square root of 5, get x by itself. Now remember, the square root of 5 is 2-ish, right? So when I think about this parabola that has a y-intercept of 4, opens up because the coefficient is positive, these 2 x-intercepts are real. So I can plot them on the number line. 3 plus 2-ish is like 5-ish, but 3 minus 2-ish is like 1-ish. So that's what that parabola looks, something like that. Okay, I'm going to go up here to do D. The only reason, so that this is completing the square very nicely. The next one is not so nice because A has a leading coefficient that is not 1. And then I've got some fraction work to deal with. So the first thing I like to do is move, as I said, move the constant over to the other side. Then I have to get a leading coefficient of 1. Then I divide the linear coefficient by 2. I square that and I add it here. And then I don't forget that I'm also, whatever I put inside this parentheses, I'm multiplying by 2. Right? The x squared is multiplied by 2, the -8x is multiplied by 2, and the 16 is multiplied by 2. Here's my perfect square trinomial. Right? And again, I do a double check to make sure. This -4 is right here. Now I need to solve this equation. I'm going to undo the division by 2. I'm going to plus and minus square root both sides. And I'm going to add 4. Notice I am not scared of the fraction, right? Square root of 5, square root of 23 over 2, whatever, right? 23 over 2 is what? 11-ish. 4 plus, right? And so the square root of 11-ish is like 3 something. So 4 plus 3 something and 4 minus 3 something. Those are the two x-intercepts for this parabola that also opens up. So that's really it. I'm just going to, here, I want to highlight that for this, I asked you to do the quadratic formula for solving, is when you do the quadratic formula on this one, you end up with 1 plus or minus the square root of a negative. That means that this parabola that opens up and has a y-intercept of 5 does not hit the x-axis. There are no real solutions. If you are just asked to solve, the answer is no real solutions. If you were asked to solve over the set of complex numbers, then yes, you are supposed to recognize that the solutions are like that, but they aren't graphed, right? This is the real number line. You don't graph those, right? You can't graph non-real numbers on a real number line. All right, this is just a regular, this is practice making sure you can factor and separate. This is another completing the square. This is a quadratic formula that the answers are real. They're just not nice. In other words, they're not rational. I do want to hit this one. Only because the completing the square, again, has some fraction work in it that might throw you. So I just want to quickly hit this before I go on to number 7. Remember, you're dividing this by 4 and you're dividing this by 4 and then pulling that 4 out front. So 6/4, right, is actually 3/2. Now, every other time I've completed the square, I've taken the linear term and divided it by 2. This is the linear coefficient, I should say. But remember, dividing by 2 is the same thing as multiplying by 1/2. And this was positive, so this is also all positive, right? I'm going to square that. I have birthed a perfect square trinomial. Right, 1 is really 4/4, right? So I just added that fraction. Now look what happens. Dividing both sides by 4. Oh, and remember, right, this plus 3/4 matches this plus 3/4. That's how I know I've done it correctly. Dividing by 4 is the same thing as multiplying by 1/4. Take the plus or minus square root of both sides. Oh, hey, 16 is a perfect square. right? Which means I can put this all together if I wanted because it has the same common denominator. Right? But again, this parabola opens up, has a y-intercept of -1, and it hits the x-axis at, let's see, square root of 13 is a little bit bigger than 4, right? And 4 divided by 4, a little bit bigger than 4 divided by 4 is 1-ish. So -3/4 plus 1-ish is positive. -3/4 minus 1-ish is negative. So it looks something like that. Okay. Swell. All right, last thing real quick is to remind you of your unit circle, and that in pre-cal, and firstly, let me say that in calculus only works is in radians. So, however, pre-calculus and physics often work in degrees. So I'm going to write the corresponding. You do need to know that 45 degrees in radians is pi over 4. Not going to change my answer. Cosine is 1/3 of pi. I'm sorry, 60 degrees is 1/3 of pi. Ooh, that should be a C, shouldn't it? And 30 degrees is 1/6 of pi, remembering that, right? All the way around is pi. So half of pi is right here. 1/4 of pi is right here. A 1/6 of pi is right here, right? Because it takes 6 of these to get over here. It takes 4 of this, right, sector to get all the way over to pi. And 1/3 of pi is right there. It takes 3 of these pieces of the pi to get all over to 1 pi, right? And of course, all the way around is 2 pi. The circumference of the unit circle is 2 pi times the radius, but for the unit circle, the radius is 1. The circumference of the unit circle is 6-ish, right? 3.14-ish times 2. All right, so some of your unit circle values that this is just drill. You need to know these. Sine of 45 or the sine of degrees or the sine of pi over 4 is 1/√2. That is the non-rationalized version, which is absolutely fine. Or you might see this, if this is multiple choice, you would see it as √2/2. The cosine of 60 degrees, remember cosine in the unit circle goes with the x-coordinate, sine goes with the y-coordinate. So sine of pi over 4, right, is the y-coordinate on the unit circle. Cosine of pi over 3 or cosine of 60 is the x-coordinate. And that's 1/2, or of course 0.5. Exactly, 1/2 is exactly 0.5. Tangent is the ratio of the y-coordinate to the x-coordinate from the unit circle. And the tangent of 30 degrees is 1/√3. Or you could see that as √3/3. These are exact values. Right? We don't give decimal approximations unless we are asked for it. Right? 0.5 is not a decimal approximation. It is exactly 1/2. All right. That's it for your second video.